what we had discussed earlier. Okay, just turn the pages of headings you must have written, and from there what topics were covered. Okay, now, so what are the topics covered till now?
Zeolite process.
Zeolite process currently covered. Before that,
Lime soda process.
okay, so external treatment, lime soda and zeolite we have covered. Now today we will see ion exchange. Now, ion exchange process is one where synthetic resins are used polymeric matrix, and they are having certain fixed charge group. Now they are termed as fixed because they remain fixed on it, and the counter ion can be exchanged. So the ion exchange process can be defined as a reversible exchange of ions between a stationary solid phase and a liquid moving phase. Coming to what is it says, so ion exchange process will provide you deionized water, and ion exchange process is defined as reversible exchange of ions. Now this is the polymeric matrix over which, like when water flows, now this is a polymer on which certain fixed charge group are there which are negatively charged, like SO3 minus. So H plus will remain over here as a counter ion. So this one is a fixed charge group and this one is a counter ion. Similarly, this is the fixed charge group which is fixed on the polymer. Now the polymer matrix is permeable to liquid or water, and you will find that when some solution flows over it, it can exchange calcium and magnesium with this H plus, and you can get release of H plus, and calcium and magnesium are retained here. So that is the basic concept of softening of water. Now demineralization means what? Not only the cations, but the anion part will also be removed. So for similar reason, you may be using some anionic resin. Anionic resin will be having a positively charged fixed charge group and a negatively charged counter ion. So that the counter ion, which is loosely like bound due to the forces of attraction, electrostatic forces of attraction, can be removed and the anion part can be retained. So if water contains calcium chloride, first the calcium is removed on the cation exchanger, and then the water is passed through the anion exchanger where chloride is retained and OH minus is released. So the H plus released from here and OH from there together forms H2O. So coming back to what is a resin and what the ion exchange process is. So the process is reversible exchange of ions between a stationary solid phase and a external liquid moving phase. Okay. So a resin is an insoluble permeable polymeric matrix which is cross-linked and having long chain organic polymer capable of exchanging ions due to presence of fixed charge group and mobile counter ions of opposite charge. Okay, now these can be prepared by like synthetically by like you go for polymerization of styrene in presence of divinyl benzene, or you use either addition polymerization or condensation polymerization, and substituted phenol formaldehyde, but not very cross-linked. Phenol formaldehyde will lead to formation of compound like a polymer like bakelite. Okay, so if you use a lesser cross-linking, then there will be formation of a softer material. Okay, so the functional groups are then introduced into the resin, and the functional groups can be introduced by treating it with acids and so on. Okay, now what are the types of resin? Strongly acidic cation exchanger resin, that is SO3H group, sulfonated polystyrene in hydrogen form. Okay, then moderately strong cation exchanger, POOH twice, weakly acidic cation exchanger, COOH, strongly basic anion exchanger are NR3 plus, or something like CH2N. This becomes the quaternary ammonium part, which is having a positive charge because one bond here and three methyl groups are attached at three. So when it attains a like it has a positive charge, the OH minus can be associated with it as a counter ion. Okay. Then weakly basic anion exchanger resin, it will be again like the whole part will be having some positive charge and a negative ion will be associated with it for the anion exchanges. Now, cation exchange resin is commonly used as styrene, divinyl, benzene, copolymers, which are on sulfonation or carboxylation become capable of exchanging. Like the fixed charge group are incorporated when you treat it by during sulfonation or carboxylation. Okay, COH. So they are represented as R. The resin, the polymeric matrix is represented as R, and the counter ion is represented as H plus. So you can consider if it is a cation exchanger resin, this R comprises of a negatively charged fixed charge group. Okay, negative fixed charge group is there in this resin. Example are amberlite, Dovex. These are the example of an exchange resin. Then anion exchange resin, materials capable of exchanging anions in um, uh, with its structure or the counter ion. And for water softening, the exchangeable anion should be OH minus ion. So when you are using water, softened water, then it should definitely be present as ROH minus because unless you have ROH minus, your cation exchanger resin is releasing H plus, so that will compensate this. This release will compensate that H plus, and it won't add either alkalinity or acidity to the water. Then anion exchanger employed for water softening are styrene, divinyl benzene, or amine formaldehyde copolymers, which contain basic functional groups such as amino, quaternary ammonium, or quaternary phosphonium, or tertiary sulfonium groups as the integral part of the resin matrix. Okay, so that is represented as R. Okay, so after treatment with NaOH, the anion part is OH minus, and the fixed charge group, as written here, all those things will be a part of R. Okay, so this is where R is the insoluble polymeric matrix and OH minus is the exchangeable ion. Then the example is amberlite 400. Now the difference between this 120 and 400 is these are the commercial name. Market में जाएंगे तो you will have to ask for amberlite or scientific company. Then Dovex 50 is cation, Dovex 3 is anion exchange. Okay. Now what is the structure of this resin?
IR,
Now, yes.
IR, Umberlite IR. That's
It is
full
the
name, no?
name. IR is not infrared. It is
Okay.
like the commercial name Amberlight IR 120, and here it is Amberlight 400. Okay, it's just the name. Okay, commercial name. Okay, now coming to the hypothetical structure of cation and anion exchanger resin. I told you like you have styrene. Styrene will be what molecule? Styrene will be like it will be CH2 double bond CH and a benzene ring. Now you sulfonate it, so sulfonation will attach SO3 minus H plus or SO3 minus group will be added to it. So you go for either use this particular monomer or you first go for polymerizing the styrene. So the styrene is polymerized and then sulfonic acid group is added to it. So this is a sulfonated polystyrene in hydrogen form, and this is a strongly acidic cation exchanger resin, and we are using it the name called Zeocarb 225. Okay, so that will be used in lab, and you perform determination of the capacity of exchange exchange capacity of ion exchange resin. Okay, then you have again, this is a polystyrene, but this is the quaternary ammonium chloride. So this is quaternary ammonium chloride. You have methyl like CH2, then N, then methyl group of where the structure is here. Okay, or like this is CH2, this is CH2N, CH3 thrice, overall positive charge, and OH minus. Quaternary ammonium strong base and ion exchanger resin. So these two structures you should be knowing, one of this and one of this. Now depending on the affinities of this is classified as a weak acid cation exchanger. This is a weak base anion exchanger, this one, and here it is a strong base and ion exchanger as in this particular thing. Okay, so small changes are there in this fixed charge group, that's all. But the counter ion, you will find that mostly it is the hydroxyl group or OH minus hydroxyl ion, and here it is H plus. Okay, then the cation exchange resin, you can imagine like it appears like I don't know whether. Wait a minute, I'll show you. Resin structure should be shown. You must have seen these things. Wait a minute, I'll show you the structure also, like actual how it looks. Okay, it is there. Now you see, okay, this is the experiment part which came up. Okay, can you see the screen? What we discussed, this part, right? Yes, can you
Yes.
hear me?
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am.
Okay, so this is the like this is again an hypothetical structure drawn showing some cross-linked like polymeric matrix with a fixed charge group SO3 minus and the counter ion is Na plus here. And when it is stored, the cation exchanger resin is stored in sodium form because it is dry, and when you are using it, you are converting into hydrogen form. So you will have to hydrate it, so it is put into HCl and aqueous solution. So a slight swelling is also seen for these particles, and these particles look like this. Can you see, like this is the experiment which we will be performing next. Now this is the ion exchange resin, very fine, just like your poppy seeds. Okay, they are fine globular particles. Okay, so that is this. So while looking into, this is a petri dish in which the resin is kept. This is 0.25 gram of resin, right? And this 0.25 gram of resin then is put into, like, this is the glass wool, and over this it is put. Okay, so what is the reaction? The resin, which is sulfonic acid group, is there. Associated initially is a sodium ion in dry condition. when you put like acid, it gets converted into like um, SO3 minus H. Now, same thing applies for if you are having a resin which is in hydrogen form. Resin in hydrogen, you can now consider B as H plus. Now, when calcium and magnesium comes into the solution, it will exchange H plus with the calcium, and the resin SO3 minus will retain the Ca2 plus or not 2 plus Ca, because once it is attached here, it will be Ca or Mg plus H plus is released. So that is what is the reaction taking place. Now, initially when it is stored, it is in the sodium form, and it releases like when it is kept in HCl for say around half an hour, it is kept in this HCl. So the resin is converted into hydrogen form. Now the resin is ready for use, which is in hydrogen form. Now you allow like the experiment comprises of this, but you can imagine here that there is calcium sulfate. So it will remove like twice here it will be Ca, and um, what will be forming H2SO4. Now this H2SO4 is then removed by your this thing, and by the anion exchanger resin will remove the SO3 minus group, SO4 minus group, 2 minus. Okay, coming to different types of resin commercially available, these are the types and no one will be asking you these things. Okay, now coming to actual process. Now such resins which are, one is cation exchanger resin and the other one is anion exchanger resin, which is put into like
Ma'am,
two
previous slide, please.
Yes, this
Previous
one,
slide, ma'am. This
this one.
previous.
Previous is from practical. We'll discuss
Ma'am,
that in
again previous.
this one.
No, ma'am. Forward one, ma'am. Yes, ma'am. Last one.
This one.
No, ma'am. Again previous. Yes.
This one.
Yes, ma'am.
These are some of the like these are the commercial names. These are the groups present, and based on these, they are classified. Now, what you appears here
Previous,
is
ma'am. Previous. Not this one.
this
This one.
one.
Yes, ma'am. This one. Yes,
A
ma'am.
principle, you see, this is an experiment which we will perform. That is your fifth experiment. And this slide is coming from that experiment. Even this slide is coming from your experiment only. Okay. So, like,
Okay.
just I wanted to show you how the resin looks like. That is why I took these slides, and I think these two came from there. Just now, I did that part too. That is why. Okay, we will again see this how to measure the capacity of an exchange resin.
Okay, ma'am.
Okay, so coming to the ion exchange process, you have like there are two columns which are stacked with gravel. Then there will be the ion exchange resin, and then you can pass hard water through it. So generally, the sequence that is followed is first the cation exchanger resin is placed, or water is allowed through cation exchange. Reason being, your cation resin is represented as RH2. Now this RH2 with when Ca2 plus plus twice Cl minus, because this will not be present as only as cation, right? It will be a salt like calcium chloride or calcium sulfate. So that part, the negative part is written here. So the negative part associated with it, you consider that this water contains Ca2 plus and Cl minus. So first of all, in this particular column, reaction that take place on the surface of this cation exchanger resin. This is a cation exchanger resin. Resin H2. H2 is the replaceable part of it or exchangeable part, H plus. So you get an exchange that RCA is formed or calcium is retained by the resin, and twice H plus is released. So the water which is moving out from this column will contain H plus. Now, not only H plus, but it contains the chloride and these parts. So what happens? This H plus, and if calcium chloride or calcium sulfate is there, so you can think that it is forming H2SO4 or HCl. So the water flowing out from here is acidic in nature. So it is necessary that your next column should be an ion exchange resin where the exchange of anion part will take place. And that is why when I told you that the resin should be for water softening, the resin should be in hydroxide form. So hydroxide form means this will exchange chloride and sulfate and carbonate to OH minus, and when OH minus is released, this OH minus and this H plus together forms a neutral molecule, that is H2O. So the water coming out from the anion exchange resin will be neutral. So what is ion exchange process? Ion exchange process utilizes the synthetically prepared ion exchange resin. To define it, ion exchange process is a reversible exchange of ions between a stationary solid phase and a liquid moving phase. And there are two types of ion exchange resins, cation and anion resin. When an ion exchange process is carried out, the water should pass through the cation exchange resin, removes the hardness causing calcium and magnesium. Not only magnesium, also removed like Fe, Mn, Al, Na, everything. Okay, and when the water passes through the cation exchange resin, all the anions which are associated with these calcium, magnesium, aluminum, and all are removed, and the water is completely demineralized, deionized water is obtained out. Now, many a times, not only these two, but one fixed bed will be there, in especially in thermal power plants, where you need a totally, completely zero conductivity. No conductivity should be there. So no sodium or any sort of ion should be there in the water. For such a thing, after passing through cation, then water passes through an anion, then water also passes through a mixed bed. Like both the things are kept together, and that the flow rate is slow. Okay. In this particular process, what you see, the ion exchange process will then be, the water will then be going to a degasifier, so that it gets like the dissolved gases are also reduced. Okay, so what is this H plus, which is formed here, and the OH minus released by the anion exchange column together forms H2O. And hence you get deionized or demineralized water. Now, ion exchange process also works in the two.
Ma'am,
The whole
here
process
will
is, yes, some doubt is there.
ma'am, here will be HCO3 minus or CO3 2 minus?
CO3 2
2 minus
minus HCO3
minus.
माइनस भी रहा तो वो भी तो एक्सचेंज होना ही है ना.
Yes, no.
Okay, then only you will
Okay.
get deionized or demineralized water. So all type of cations are removed by cation exchanger resin. All type of anions are removed by anion exchanger resin, and you get deionized water. Okay.
कैल्शियम कार्बोनेट का तो पीपीटी बन जाता है ना.
Yes.
कैल्शियम कार्बोनेट का तो पीपीटी बन जाता है ना, हमको उसका तो कार्बोनेट नहीं हो सकता है, मैग्नीशियम का हो सकता है.
कैल्शियम कार्बोनेट का पीपीटी कब बनेगा? सबसे पहले आपने जो भी सोल्यूबल कैल्शियम सॉल्ट है वो जब यहाँ से जाएंगे तो कैल्शियम रिटेन हो जाएगा ना यहाँ पे. समझ में आ रहा है?
कैल्शियम कार्बोनेट तो हम सोल्यूबल नहीं है ना.
तो कैल्शियम कार्बोनेट तो जहाँ जिस टैंक में से आप इसको पानी लोगे वहीं पे सेटल हो जाएगा ना नीचे का, अगर कैल्शियम कार्बोनेट है तो, क्योंकि वो तो इनसॉल्युबल सॉल्ट है. तो आपके कैटायन एक्सचेंज कॉलम में आएगा ही नहीं कैल्शियम कार्बोनेट. वहीं पे टैंक में ग्रेविटी के से नीचे सेटल हो जाएगा. तो पानी उसमें क्या है, उसमें सोल्यूबल सॉल्ट्स ऑफ कैल्शियम एंड मैग्नीशियम आते हैं.
यस,
ठीक है,
क्लियर मैम. ओके मैम.
ओके, ठीक है. और अगर कैल्शियम कार्बोनेट बनना भी है तो पहले तो मैग्नीशियम, ये प्रोसेस, दिस process of water softening relies on the principle that the hardness causing salts are getting exchanged with the and are read the resin on the surface of resin. अभी आपको ये structure जो दिखाया है, this is hardness, hard or very hard or very hard water. You should not put into direct ion exchange resin. 2 लीटर में ही resin exhaust हो जाएगा. जो पानी आपका लाइम सोडा प्रोसेस से ट्रीट होके आया है जिसमें हार्डनेस बहुत कम है, उसी पानी को जनरली या फिर ऐसा कोई फ्रेश वाटर बॉडी जहां से पानी आ रहा है तो लाइक इट इज कंटेनिंग लेस ऑफ हार्डनेस, such lesser hardness water can be should be this also works in the two alternating cycle. One is softening run and the other one is regeneration run. अभी जो हमने देखा ये softening run था, यहाँ पे softening हुआ, यहाँ पे complete removal of all type of anions हुआ. That is why it is demineralized deionized water. Okay. Now what is there? A time reaches that this resin ये जो डाल के रखा है यहाँ ये completely exhaust हो जाता है. Completely exhaust यानी everything is RCA or RMG and everything here is RCl2 or RSO4 or RCO3. Things are clear? So you need a regeneration. So for regeneration, what is done? The supply of raw water is stopped and dilute HCl is added at the top of the resin and it is allowed to remain there for some time. And then here in this particular case, some NaOH, some 10% NaOH is added, the raw water supply is stopped and the NaOH is allowed to remain here. After say 1 hour, the whole thing is reacting and the washings are collected separately into it. So when these washings are collected, the calcium magnesium will be coming out as if you are adding HCl. Here are the reaction. When the resin is exhausted, it loses its H plus and OH minus and the capacity to exchange the ions. Therefore, this RCA, this is the cation exchanger. So this is treated with either HCl or H2SO4. You get back RH2 resin in hydrogen form and releases CaSO4 or CaCl2, MgSO4 and MgCl2. So the washings that are collected here will contain this particular thing. Okay. So this which is removed from a large quantity of water, say 1 million liters of water, now is coming out into like say just like 1 liter, 2 liter, 5 liters of something which is being removed separately. Then the anion exchanger resin is treated with NaOH solution so that the resin which is in which has been exhausted forming RSO4 or RCl2 with NaOH, it reacts and forms ROH twice plus Na2SO4 NaCl. So when you go for like when you stop the raw water supply and add NaOH, some few liters of NaOH is sufficient and then you wash it nicely and collect the washing separately here. So you have this will regenerate the resin which is exhausted, the anion exchanger resin which is exhausted. Now it is in when treated with like 10% solution of NaOH, the resin is regenerated back as ROH twice. So please keep in mind that because your calcium and magnesium are divalent, the resin is termed as RH2 and ROH twice. So there is no confusion with this. So when you write as RH2 and ROH twice, this is the cation exchanger resin, this is the anion exchanger resin. When it gets exhausted on exchanging these, you need to go for regeneration. How to regenerate? By adding acid to the cation exchanger resin, where the acid will react with this, release the calcium and magnesium, and RH2 is regenerated or reformed. And the anion exchange column, you add NaOH. So when you add NaOH to the anion exchange column, this exhausted anion exchanger resin is uh, converted into ROH twice. Things are clear? Okay. So what are the advantages? The process, Yes.
मैम डायग्राम पूछते हैं एग्जाम में वो?
डायग्राम ड्रॉ करना पड़ता है, रिएक्शंस लिखनी पड़ती है, आयन एक्सचेंज प्रोसेस पूछा तो ये लिखना पड़ता है, what you have to write these reactions as well as, because this is half of the process, right? This is the softening run, but softening run अधूरा है अगर आपने ये reaction नहीं लिखे तो आपको half the marks मिलेंगे. You will say madam this and this are totally what you say, vice versa, like यहाँ पे calcium is retained by this and H plus is released. Here H plus is retained and calcium is released. But still, you have to show that these are the reactions by which the resin is regenerated. So separately for cation exchange or resin, uska regeneration लिखना है. You can write, if you have less time, you can write at least for one. Okay, calcium or magnesium with one of the acid. Here also. Okay. Now, what are the advantages? The process can be used to soften highly acidic or alkaline water. Unlike zeolite process, the soft water does not contain sodium salts. So rather it is deionized water. There is no ions present. It removes all cation and anion other than H plus and OH minus. All ionizable impurities are removed. It produces water of very low residual hardness. Still the residual hardness is there, 2 ppm. Okay. So disadvantages. The process is expensive. Both the equipment and the resin are costly, and regeneration cost is also high. So turbid water decreases the efficiency of process because it clogs the upper layer. Turbidity will block the upper layer, right? So it will clog and the process will be little slower. That will affect the rate of softening process. Okay, so these are some of the advantages and disadvantages. Then you can have a comparison of lime soda, zeolite, and ion exchange process, or you can compare the zeolite and ion exchange process because that is cation exchange process. This is total ion removal process. Okay, then. So the questions are asked there, like comparison or some twisted question regarding like how this is better and that is not better and so on. Okay. Now, once the external treatment is over, the next part is internal treatment. Now, water after we see here I say that when you are जब आपके पानी में बहुत ज़्यादा hardness है, raw water is hard, like 200 ppm, you see 200 or 250 ppm. Then the water is treated first with lime soda process, brought down the residual hardness, then it is fed into the ion exchange process. Now ion exchange process से भी जब बाहर निकलेगा तो it is having some 2 ppm of hardness. Now what happens, like this 2 ppm of hardness, when it goes into the boiler, continuous boiling and steaming के वजह से this 2 ppm goes on increasing and scale sludge may form. So because of that, there is another treatment, one more, that is termed as internal treatment. It is also termed as conditioning. So this comprises of adding some chemicals inside the boiler so that scale formation is avoided. So internal treatment is adding chemicals inside the boiler so that scale formation does not take place. Rather than scale, it will form sludge. If some salts are there, they will form sludge because sludge are easy to remove and scales are difficult. So it is also called a sequestration or conditioning. It involves treatment inside the boiler by adding the suitable chemicals which either precipitate the scale forming impurities or they which precipitates as scale. uh, the scale forming impurities are converted into sludges. So these chemicals will convert the scale forming impurities into sludge forming, which can be removed by blowdown operation. Convert them into compounds which will stay in dissolved form in water and thus do not cause scale or any harm. The first one is carbonate conditioning. Now this is an old one which was used for low pressure boilers. क्योंकि लो प्रेशर बॉयलर में जो आपका कैल्शियम कार्बोनेट बनता है, कैल्शियम कार्बोनेट will remain as sludge. The moment the boiler is operating at high pressure, even the calcium carbonate precipitates as scale. So, like due to high pressure, this will stick to the walls very adherently, coherently, without porosity, and that is how the this particular uh, conditioning was used for low pressure. In low pressure boiler, the scale formation can be avoided by adding sodium carbonate to boiler water. So when you add, like, if there is water which is saturated with calcium sulfate, okay, due to continuous evaporation, then you add sodium carbonate to it. So when sodium carbonate is added little quantity, calcium will come out as calcium carbonate, and calcium sulfate will not be precipitating out because the ionic product of calcium carbonate is attained. So, for a salt to be precipitated, sufficient amount of ions forming the salt must be present so that the product of their concentration exceed a limiting value known as the solubility product. Thus, for a salt like calcium carbonate to be precipitated, the product of the concentration of calcium and carbonate ion must exceed the solubility product of CaCO3, that is KCaCO3. The formation of calcium carbonate may be represented by this equation. This is say 1. When the equilibrium is established between the like this and this, you will find that um, this is calcium sulfate. Now you consider that water is saturated with both calcium carbonate as well as calcium sulfate. Now in such condition, if you add little of sodium carbonate, so adding little of sodium carbonate will maintain the concentration of carbonate ion more. And if this is maintained more, then the Ksp of calcium carbonate is achieved and the Ksp of calcium sulfate is not achieved. So similarly, like if sodium carbonate is added, the carbonate increases. Then in order to maintain the Ksp of CaCO3 constant, the some calcium will get precipitated. Like so, the Ksp of calcium sulfate is not attained. Here you like divide the equation 1 by 2, the carbonate ion concentration by sulfate ion concentration. If this carbonate ion concentration is maintained high, you equate it to K dash, another constant. And if this is high, maintained high, your Ksp of calcium sulfate will not be attained. So, or when the carbonate ion concentration is more than K dash SO4 2 minus ion concentration, then only calcium carbonate will be precipitated in preference to calcium sulfate because the solubility product of calcium sulfate cannot be attained under these conditions, under the conditions of high carbonate concentration. Okay, thus the deposition of scale forming calcium sulfate is prevented, and carbonate conditioning is used only for low pressure boilers. In high pressure boilers, the excess sodium carbonate might convert it to NaOH, causing caustic embrittlement, and this calcium carbonate also deposits at scale in high pressure boiler. Okay, then this is an important part, that is phosphate conditioning, because this operates for low pressure as well as high pressure boiler. Now, when water is added inside the boiler, um, just now we have seen that if you maintain a high concentration of this, this will not persist. Similar concept is used here. So what is used? All the calcium which is present, whether it is calcium chloride, calcium sulfate, anything, all the calcium which is present here is treated with sodium phosphate, and it leads to formation of calcium phosphate. Now the calcium phosphate which is formed here, it forms sludge and can be removed by blowdown operation. So phosphate conditioning is used equally in low and high pressure boilers. Phosphate reacts with calcium and magnesium salts, forming loose sludge of calcium and magnesium phosphate, which can be removed by blowdown operation. The overall reaction is thrice CaCl2 plus twice Na3PO4. Now this Na3PO4, it may be um, sodium dihydrogen phosphate or sodium hydrogen phosphate or sodium phosphate. Like depending on the pH of water, you can use this. So this reacts with Na3PO4 forming Ca3PO4 twice plus 6 NaCl. Now this calcium phosphate, if you consider that an equilibrium has been attained with calcium phosphate and calcium sulfate. So both of them are in equal proportion. So calcium phosphate Ca 2 plus raised to 3 because there are uh, three calcium atoms. And phosphate 3 minus is the valency raised to 2. This is twice, no? So is equal to KSP Ca3PO4 twice. So this is the solubility product. Now the solubility product, if you divide the powers by 3, this will be 3 by 3, that will be 1 and 2 by 3 and 1 by 3. Now you consider if sodium phosphate is added, the phosphate ion concentration increases and maintains the KSP of calcium phosphate constant and the precipitate and precipitates as calcium phosphate sludge. Similarly, in a solution saturated with calcium sulfate, the KSP of now when both the things are there, if you add a little excess of sodium phosphate, the phosphate ion concentration will be so high or will be maintained high than the sulfate ion concentration that even if you consider that the water is saturated with calcium sulfate and calcium phosphate and they are in equilibrium because of high concentration of phosphate ion, calcium sulfate or calcium will not combine with sulfate and precipitate out, but calcium will always, in preference, will combine with phosphate, forming calcium phosphate, and that will be precipitating out. And that, yes, will precipitate, but that will be remaining. No, it will not stick. It will remain as loose and slimy sludge, and thus that can be removed by blow down operation. So that is the basic concept behind it. So from this it is clear that if phosphate ion concentration is more, that is if phosphate by sulfate ratio is more than your constant value of these solubility products, or in other language you say that the phosphate ion concentration is maintained higher than the constant into the concentration of sulfate ion, then only calcium phosphate will be precipitated in preference to calcium sulfate because the solubility product of calcium sulfate cannot be attained under these conditions. Okay, so it will not, calcium will always precipitate as calcium phosphate. So magnesium chloride, which hydrolyzes to magnesium hydroxide scale, can be removed by adding appropriate sodium phosphate like sodium dihydrogen phosphate or sodium hydrogen phosphate or Na3PO4. Now it depends on the pH of water sample. If the water sample is alkaline in nature, then you will use sodium dihydrogen phosphate because this is having H plus. So for alkaline water, you are using sodium dihydrogen phosphate. For acidic water, sodium trisodium phosphate. Then neutral water, disodium hydrogen phosphate is used. So depending on this, you can use this. Then the third type of compound that can be added is termed as colloids. Now, colloidal conditioning should be in optimum because the basic principle of colloidal conditioning is the colloidal conditioners will go and encapsulate the precipitate formed. So it allows formation of a precipitate, but the particle of precipitate which is formed is covered by this glue or agar-agar or tannin, starch or seaweed extract. So it covers completely. So the basic principle is of the colloidal conditioning is it covers uh, or surrounds the precipitate form and does not allow it to stick to the walls. Rather, that can be removed by blowdown operation. So that is the basic principle of colloidal conditioning. And the conditioners that they are used conditioning agents are glue or agar-agar or tannins, starch, and seaweed extract and all. Okay, so the principle is totally different. So what is the principle in the first case? Principle is scale forming salt is converted into sludge forming salt, but this works only in low pressure boiler. In high pressure boiler, your scale forming salt is converted into sludge forming salt, and this works in high pressure as well as low pressure boiler. Then third one is colloidal conditioner. Here the principle is the precipitate which is precipitating out in the boiler water is covered by these colloidal conditioners, and they don't they make it like loose or very like, because of this they don't stick to each other nor to the walls, so it remains as suspended in the water, and that can be removed by blowdown operation. Then the fourth one is Calgon conditioning. Now, Calgon is sodium hexametaphosphate. Now, this sodium hexametaphosphate can be written as Na2, Na4, PO3 six times. So, this sodium hexametaphosphate ionizes as twice Na plus and Na4 PO3 six times with 2 minus charge. Now, this forms a complex which is soluble complex. So, a water soluble complex of calcium phosphate is formed, and you get formation of Na2SO4. So what all calcium is present in water will be reacting with this, forming a soluble complex of Na2Ca2PO3 six times, and that is how it is not precipitating out as K. So the basic principle of Calvin conditioning is treating the boiler feed water with sodium hexametaphosphate, which reacts with the scale forming salts, producing a water soluble complex, and thus calcium, which may precipitate out as clay, is converted into a soluble complex which remains in water.
Then phosphate is PO4 3 minus.
Yes,
Phosphate is PO4 3 minus now and PO3 also.
PO,
4 3 minus.
PO4 3 minus.
Yes, ma'am, phosphate.
Okay, then you write the general formula. Okay,
Yes, ma'am. This is given in this PO3 whole 6 hexametaphosphate.
yeah,
PO3.
this is sodium hexametaphosphate, PO3
Yes, ma'am.
6 times.
Okay.
Okay, so you are getting a soluble complex ion formed here, and it is in ionic form. So you get so you don't get any scale or sludge formation. Then the fifth type of conditioning is with conditioning with EDTA. Just like this, you add EDTA, ethylene diamine tetraacetic acid. It reacts with calcium magnesium salts, producing a soluble complex. It is written here. Phosphate treatment fails to prevent the formation of iron oxide and cuprous depositions. Hence, conditioning with complexing agent like EDTA secures scale-free and sludge-free operation of boiler units as it forms a soluble complex with metal cations. So you know we have already seen calcium EDTA and magnesium EDTA complex. It is water soluble. So calcium and magnesium remains in water with EDTA and does not lead to scale formation. Okay. So things are clear? Okay. Now, before we close today, what things we have? We started with this slide where impurities, fluoride, nitrate, arsenic in drinking water, and alkalinity and hardness in industrial water. How to determine it and what are their cause and effect that we have seen. Removal also we have seen. Then, if you use impure water in boiler for steam generation, there are certain troubles caused to the boiler, carryover, caustic embrittlement, corrosion, and scale and sludge formation. To avoid this, we go for a treatment. Now, that the treatment is divided into two. One is external treatment, and the other one is internal treatment. The external treatment is divided into two. One is lime soda process, the other one is ion exchange process. Lime soda process is divided into, like, you can classify them as batch, continuous, hot and cold lime soda process. And the ion exchange process, you have a zeolite process, which is only cation exchanger is exchanging process. And the second one is an ion exchange process where cation as well as anions are removed. So you get demineralized water here. Then coming to the internal treatment, apart from external treatment, some internal conditioning is also carried out. So internal conditioning is carbonate conditioning, phosphate conditioning, Calvin conditioning, colloidal conditioning, and conditioning with EDTA. So what now remains is only domestic water treatment, sedimentation, coagulation, filtration, sterilization, and breakpoint chlorination. So on Saturday we will complete the chapter. Saturday we have class 12 to 1. I'll engage the class and we will complete this part also. So with this, your water treatment chapter will be completed. Things are clear?
Ma'am, can
Ma'am,
you show the
could you
previous
repeat
slide?
please, ma'am, about turbidity,
Which
how efficiency decreases, ma'am?
yes?
How rate of efficiencies decreases, ma'am,
How the
by the turbidity?
ion exchange process decreases.
Yes,
Yeah.
ma'am.
Now, when you prepare a bed of ion exchange resin, the surface of the bed, if the turbidity, what is turbidity? Turbidity is fine particles which are having negative charge on it, and they are fine particles, and these resin which we say are permeable. So these the turbidity particles, or the particle of size 10 to the power minus 4 to minus 7 centimeters, they go and block the pores of these resin and like the voids which are there. Now once that is occupying the voids and going into the this particular permeable polymeric matrix, they will go and stick. So definitely the resin particle is not completely exposed for the exchange of ions, and that is why the efficiency will go down. You can just imagine big balls, okay, of
Okay.
and through which you are passing, but the ball is permeable, like the polymeric matrix, like the liquid can trickle through in between. So, or like it's a wool ball, woolen ball. And when you put it in water, the surface of wool can exchange the ions. If you have lot of particles, particulate matter in your turbidity in it, the wool ball will be covered with all muddy particle, and water will not go inside, nor the any exchange of ions will be taking place. Okay.
Okay, ma'am. Clear, ma'am.
Ma'am,
Clear, ma'am.
ma'am,
Okay, anything else?
Yes, ma'am, can you show
ma'am,
the
can you
previous
get
slide?
of the slides from starting?
Thank you,
Hello,
ma'am.
hello.
Yes.
Can we get the PDF of slides from starting now?
This PDF.
Yes, ma'am.
No, this theory PDF, theory book is there. Read from the book. Practicals PDF I gave because you see, like exact normality, molarity solution, how much was added. Because you are not in college, that is your disadvantage. Like that is a drawback. तो अगर आप कॉलेज पे होते तो हमने पीडीएफ भी नहीं दिया था. It is only orally explained with the chemical reactions written on board, and rest of the things students only are doing. But here everything, like all the things, even the observations are written and given to you. Things are clear. So note PPT for the theory class will be provided. You have to read. If you have any doubt regarding anything, I'll give you the book PDF, book images. We can discuss here and why it is mentioned like that. Okay, things are clear. So we close today here. Saturday we are meeting again. Saturday we will have class.